Right now, you are surrounded by darkness. Not the familiar darkness of a closed room or a moonless night, but an absolute void that extends 13.8 billion years in every direction. The James Webb Space Telescope pierced that darkness deeper than any instrument in human history. And when it looked into the ancient abyss, something impossible stared back. The void is not empty. It never was. In December 2021, humanity launched a machine worth $10 billion into orbit a million miles from Earth. The James Webb Space Telescope carries a mirror 21 feet across, plated with gold to capture infrared radiation so faint it would take 1 trillion years for your eye to register it. The mission parameters were clear. Look backward through time. Find the first galaxies. Understand cosmic dawn. Map the birth of structure in a universe that was supposed to be simple, predictable, governed by laws we had mastered. Webb began sending data in July 2022. Within weeks, cosmology was in crisis. The telescope found galaxies that should not exist. Massive, mature star systems glowing in the universe's infancy, formed when the cosmos was barely 300 million years old. These were not infant galaxies taking their first stumbling steps. They were giants, fully formed cosmic metropolises containing hundreds of billions of stars, organized into elegant spiral structures. Blazing with the chemical signatures of multiple generations of stellar evolution, the problem is simple and terrifying. There was not enough time for these monsters to grow. Picture trying to grow an adult human from a fertilized egg in 3 weeks instead of 9 months. The biological mechanisms cannot operate fast enough. Cells cannot divide, differentiate, and organize into organs and systems within such compressed timescales. The same impossibility faces galaxy formation in the early universe. Stars need time to form from collapsing gas clouds. Those stars need time to live, fuse elements, and die in supernova explosions. The scattered heavy elements need time to coalesce into new stellar generations. This cycle repeats, each iteration building complexity. Standard cosmological models predict this process requires at least 500 million years to produce galaxies containing significant stellar populations. Webb found them at 300 million years, at 200 million years, at 200 million years after the Big Bang. Erica Nelson, an astrophysicist at the University of Colorado, was examining postage stamp-sized sections of Webb's deep-field images when she spotted the anomalies. Fuzzy red dots that looked impossibly bright for their distance. She ran the numbers again. The redshift measurements confirmed what the images showed. These objects existed when the universe was approximately 3% of its current age. Their luminosity indicated stellar masses approaching 100 billion solar masses. Each one contained nearly as many stars as the entire Milky Way. The team informally nicknamed them universe breakers. The name is not hyperbole. These galaxies break the standard model of cosmology that has successfully explained observations for decades. The lambda cold dark matter framework, which accounts for cosmic microwave background fluctuations, large-scale structure formation, and elemental abundances, cannot produce such massive galaxies so early in cosmic history. Computer simulations running on the world's most powerful supercomputers, using physics refined through thousands of observational tests, have attempted to recreate the early universe billions of times. They almost never generate galaxies this large at these epochs. The probability is less than 1 in 10,000. Joel Leha, an astronomer at Pennsylvania State University, captured the magnitude of the crisis perfectly when he stated that discovering these objects creates genuine problems for science. But the universe breakers were only the first crack in the foundation. Webb's surveys of deep space revealed layer after layer of impossible phenomena, each more disturbing than the last. 6 months into operations, the telescope identified supermassive black holes wandering through the cosmos without galactic hosts. These are not stellar mass black holes, the compact remnants of dead massive stars. These are monsters containing tens of millions of solar masses. These objects that standard formation theory says should only exist at the centers of massive galaxies, grown over billions of years through accretion and mergers. Webb found them alone, naked, drifting through intergalactic space like cosmic refugees fleeing some catastrophe we cannot see. The most prominent example, designated QSON, contains 50 million solar masses compressed into a region smaller than our solar system. It exists 600 million years after the Big Bang, an epoch when the universe should have barely begun forming its first stars. Roberto Maiolino at Cambridge University described the object as completely off the scale. To reach such enormous mass so quickly requires either direct collapse black hole formation, where massive gas clouds bypass stellar evolution entirely and collapse straight into black holes, or primordial black hole formation, where these monsters were created in the universe's first seconds through violent density fluctuations in the quantum foam that preceded matter itself. Both explanations are terrifying. Direct collapse suggests the early universe was capable of creating gravitational catastrophes on scales we never imagined. Primordial formation suggests that black holes older than stars have been lurking in the cosmic darkness since the moment of creation, waiting billions of years for light itself to ignite. The void looked back. But it was not empty. It was filled with ancient monsters we never predicted. Andrea Ferrara's team at the Scuola Normale Superiore in Pisa proposed a radical hypothesis that explains Webb's observations while fundamentally restructuring our understanding of cosmic history. What if black holes, not stars, were the first significant sources of light in the universe? What if primordial black holes formed less than 1 second after the Big Bang were already feeding on the earliest gas clouds, lighting up the cosmos before stellar nucleosynthesis even began? The evidence supports this nightmare scenario. Many bright objects in Webb's deep field images appear point-like rather than extended, suggesting compact sources like black holes rather than distributed stellar populations. The spectroscopic signatures show emission patterns consistent with superheated accretion disks, not star formation regions. When gas approaches a black hole's event horizon, it accelerates to relativistic speeds, heats to temperatures exceeding 10 million Kelvin, and radiates across the electromagnetic spectrum with characteristic signatures that Webb's instruments can identify. These primordial feeding events would have solved the timing problem. Black holes with a 500 million year head start could easily reach supermassive status by the time the first galaxies formed. They would serve as gravitational seeds, pulling in dark matter and ordinary matter, creating the wells around which galaxies assembled. The current model assumes stars form first, then die to create black holes, which then grow slowly. Primordial black hole cosmology inverts this sequence. Black holes first, light first, stars later. But accepting this model requires confronting an unsettling possibility. If primordial black holes were common in the early universe, they might still be out there, invisible, undetected. Ancient relics from the universe's violent birth that predate every star we can see. Some could be wandering through our own galaxy, dark predators moving through the stellar population, like sharks through a school of fish. The expansion crisis deepened as Webb continued its surveys. The telescope confirmed what Hubble had detected, but could not definitively prove. The universe is expanding at two fundamentally different rates depending on where and how you measure it. This should be impossible. Cosmic expansion is a global property of space itself, a phenomenon driven by the energy density of the universe and the curvature of space-time. It should be uniform across all locations and all measurement methods. It is not. When astronomers use Cepheid variable stars and Type Ia supernovae to measure the local expansion rate, they calculate a Hubble constant of approximately 73 kilometers per second per megaparsec. When they analyze the cosmic microwave background radiation, the ancient light released 380,000 years after the Big Bang, and feed that data into cosmological models, they calculate a Hubble constant of approximately 67 kilometers per second per megaparsec. The 9% discrepancy has reached 5 sigma statistical significance. In particle physics, 5 sigma is the gold standard for claiming a discovery. It means there is less than a 1 in 3.5 million chance that the discrepancy results from random statistical fluctuations. The measurements are real. The contradiction is real. Adam Rees, who won the Nobel Prize for discovering cosmic acceleration in 1998, led the team using Webb to examine over 1,000 Cepheid variable stars across 5 galaxies spanning 130 million light-years. The precision was unprecedented. Webb's infrared sensitivity allowed measurements through dust that obscures visible light. The near-infrared camera captured stellar pulsations with accuracy that eliminated systematic errors that plagued previous studies. The result remained unchanged. The local universe expands faster than cosmic history predicts. Two possibilities emerge from this crisis, and both shatter our understanding of reality. First possibility: dark energy, the mysterious component comprising 68% of the universe's energy density and driving accelerating expansion, is not constant. It evolves over time or varies across space, creating regions where expansion proceeds faster or slower than average. If true, the cosmological constant that Einstein introduced and later called his greatest blunder might be wrong. Dark energy could be a dynamic field, changing its properties as the universe ages, creating a cosmos far more unstable and unpredictable than current models assume. Second possibility: our fundamental understanding of gravity breaks down on cosmological scales. General relativity, which has passed every experimental test in solar system environments and binary pulsar systems, might fail when applied to the universe's largest structures. Modified gravity theories like MOND, or theories involving extra dimensions, could explain the expansion discrepancy without invoking evolving dark energy. But accepting modified gravity requires abandoning Einstein's framework that has successfully explained cosmic phenomena for over a century. Neither option is comfortable. Both suggest that something fundamental about our cosmic model is catastrophically wrong. The void was looking back with questions we cannot answer. Deep in the early universe, Webb discovered atmospheric chemistry that violates every principle of planet formation. The planetary disk around a young star designated XUE-10 in the star-forming region NGC 6357 contains almost no water vapor. Instead, the inner regions where terrestrial planets typically form are dominated by carbon dioxide, creating an environment unlike anything predicted by formation models. This discovery shatters assumptions that have guided planetary science for decades. Water is one of the most abundant molecules in the universe. Oxygen is the third most common element. Hydrogen is the most common. When you have abundant hydrogen and oxygen in the cold outer regions of a protoplanetary disk, you get water ice. That ice-coated dust provides the building blocks for planets, delivering water to rocky worlds during their formation. Every model of Earth's development assumes water delivery from icy planetesimals that formed in the outer solar system and migrated inward through gravitational interactions. XUE-10's disk throws this entire framework into chaos. When Webb examined the system using its near-infrared spectrograph, astronomers expected to see the characteristic absorption lines of water vapor. Instead, they found carbon dioxide dominating the spectral signature. Water is so scarce it barely registers above the noise. Two mechanisms could create this bizarre chemistry, and both have disturbing implications. First, intense ultraviolet radiation from either the host star or nearby massive stars has sterilized the disk, photodissociating water molecules and driving away the hydrogen while leaving oxygen to combine with carbon. This suggests that planet formation around stars in active star-forming regions might systematically fail to deliver water, creating dry worlds incapable of supporting liquid water oceans. Second, the dust grains in the disk are coated with carbon dioxide ice rather than water ice due to unusual temperature and pressure conditions. This implies that planetary formation chemistry can follow pathways completely different from our solar system's history, potentially creating entire classes of planets operating under chemical regimes we have never encountered. The XUE-10 system represents a natural laboratory for alternative planetary formation. If ultraviolet sterilization is common, vast numbers of potentially habitable worlds might never receive the volatile compounds necessary for life. The galaxy could be filled with arid, carbon dioxide-rich planets formed under conditions hostile to biology as we understand it. These worlds would have geology, atmospheres, and surface chemistry fundamentally different from Earth, operating according to rules we must derive from first principles rather than extrapolating from our local example. But the strangest atmospheric discovery came from a world so extreme it challenges the definition of planetary atmosphere itself. 55 Cancri e orbits its host star so closely that 1 year lasts 18 Earth hours. The planet is tidally locked, presenting the same hemisphere to its star eternally. The dayside temperature exceeds 400 Kelvin, hot enough to melt rock and vaporize most known materials. The night side plunges into eternal darkness, cooling to temperatures potentially below 1000 Kelvin. By every rule of atmospheric physics, this hell world should have lost its atmosphere billions of years ago. Solar wind from the nearby star should have stripped away any gases, leaving a barren surface bombarded by radiation. Webb discovered the impossible. This planet maintains an atmosphere composed primarily of carbon monoxide and carbon dioxide. The discovery emerged from thermal emission measurements using Webb's mid-infrared instrument. When astronomers measured radiation from the planet's dayside, they found it was approximately 300 Kelvin cooler than models predicted for an airless body. Something was blocking stellar radiation and redistributing heat. That something could only be a substantial atmosphere capable of transporting energy from day to night through atmospheric circulation. The Hell planet's atmosphere creates one of the most extreme weather systems ever observed. Computer models suggest winds exceeding 5,000 kilometers per hour howl across the terminator, the boundary between eternal day and eternal night. These supersonic winds carry vaporized silicates and metals from the dayside, where rock boils into gas, to the night side, where temperatures allow condensation. The result is rain, made of molten minerals. Droplets of liquid stone and metal fall through a carbon dioxide atmosphere before striking the surface and flowing like lava toward the dayside, where they evaporate again to repeat the cycle. The atmosphere cannot be primordial. Any gases remaining from the planet's formation would have been stripped away within the first few million years. Instead, researchers believe this is a secondary atmosphere, constantly bubbling up from the planet's interior. The intense tidal forces from the nearby star heat the planet's mantle through friction, causing carbon-rich materials deep underground to outgas continuously. The atmosphere is simultaneously being destroyed by stellar radiation and replenished by volcanic processes operating under conditions that would vaporize most known geological materials. This creates a hellish equilibrium. Rock vapor rises from the molten surface, supersonic winds transport it around the planet. Minerals condense and rain down on the night side. The cycle repeats endlessly, powered by tidal forces that will persist as long as the star burns. The planet has become a massive distillation apparatus, operating at temperatures that push the boundaries of thermodynamic stability. The existence of 55 Cancri-E's atmosphere suggests planets can maintain gases under far more extreme conditions than previously thought possible. This has profound implications for atmospheric retention on worlds we have classified as uninhabitable. If atmospheres can survive in such hellish environments, they might also persist on planets subjected to intense radiation, extreme temperatures, or violent stellar activity. The definition of potentially habitable worlds might need expansion to include environments that would vaporize conventional planetary surfaces. But atmospheric mysteries were just one category of impossible observations Webb was accumulating. The telescope's surveys of rogue planets revealed phenomena that suggest free-floating worlds might be far stranger than anyone imagined. The Orion Nebula contains over 500 Jupiter-mass objects that do not orbit any star. These rogue planets were likely ejected from their birth systems through gravitational interactions, cast into the eternal night of interstellar space. What makes them truly bizarre is that many travel in pairs, orbiting each other at distances ranging from 25 to 400 astronomical units. Scientists call these paired wanderers jumbos, Jupiter-mass binary objects. The formation of binary planets challenges every model of planetary system dynamics. Planets typically form in circumstellar disks through accretion processes that favor single objects. Creating gravitationally bound pairs requires specific initial conditions and dynamical interactions that should be exceedingly rare. Yet Webb has found dozens of these cosmic couples. The mystery deepened when radio telescopes pointed at several jumbos detected emissions at gigahertz frequencies, thousands of times higher in pitch than FM radio signals. On Earth, emissions at these frequencies come from technological sources or extremely energetic astronomical phenomena like pulsars and magnetars. Finding them from rogue planets suggests these worlds are experiencing physical processes that do not exist in our solar system. The radio emissions appear linked to the binary nature of these objects. When two massive planets orbit each other, their magnetic fields interact, creating electrical currents in the conducting plasma that surrounds them. Think of it as cosmic friction generating electromagnetic radiation through mechanisms analogous to the aurora on Earth, but operating at scales and energies far beyond terrestrial examples. Different jumbo pairs produce different radio signatures, suggesting each binary system has unique electromagnetic properties determined by orbital parameters, magnetic field strengths, and atmospheric compositions. Some emit steady streams of radio waves. Others produce sporadic bursts following no apparent pattern. The emissions indicate that rogue planets might maintain active magnetospheres powered by their orbital dynamics rather than stellar wind interactions. The implications are unsettling. If these orphaned worlds can generate radio signals this powerful, their magnetic fields might be orders of magnitude stronger than anything in our solar system. These fields could create radiation environments around the planets intense enough to affect nearby star systems. Even more disturbing, if hundreds of jumbos exist in just one nebula, there could be billions scattered throughout the galaxy, each representing a failed solar system where gravitational chaos ejected planets into the void. These rogue worlds exist in perpetual darkness. Their only heat comes from the slow radioactive decay in their cores and the tidal forces generated by their orbital dance. They will drift through interstellar space for trillions of years, slowly cooling toward absolute zero, carrying with them whatever secrets their radio signals encode. But the rogue planets were merely cosmic curiosities compared to what Webb found when it examined the large-scale structure of the universe itself. The telescope revealed a pattern that should not exist, a pattern that suggests the cosmos was born with properties we never predicted. Astronomers analyzing 263 galaxies captured during Webb's Advanced Deep Extragalactic Survey found something impossible. Galaxies separated by millions of light-years, far too distant to have any gravitational influence on each other, are rotating in coordinated patterns. Think of discovering that every windmill across an entire continent turns in exactly the same direction, even though there is no wind pattern that could coordinate their motion. The galaxies are participating in a cosmic choreography that defies our understanding of structure formation. Leo Shamir, a computer scientist at Kansas State University, led the analysis identifying this phenomenon. The galaxies show preferential rotation directions that correlate across vast cosmic distances. This should be impossible according to standard cosmological models. If the universe is isotropic and homogeneous on large scales, as the cosmological principle requires, galaxy rotation directions should be random. When you average over volumes hundreds of millions of light-years across, there should be no preferred orientation. Equal numbers of galaxies should rotate clockwise as counterclockwise from any given viewing angle. Webb's data violates this expectation. The observations show systematic deviations from randomness that cannot be explained by statistical fluctuation or observational bias. Galaxies across huge regions of space are spinning in similar directions, suggesting the universe itself has a preferred rotational axis. Two explanations exist for this phenomenon, and both shatter fundamental assumptions about cosmic structure. First, the universe was born rotating. If the Big Bang itself possessed angular momentum, it could have imprinted a preferred rotational direction on all subsequent structure formation. This aligns with black hole cosmology theories suggesting our observable universe might be the interior of a massive black hole within a larger parent universe. If true, the rotational patterns Webb observed could be evidence of the parent black hole's spin, transmitted across cosmic scales through mechanisms we do not understand. Second, if the universe was not born rotating, then existing theories about cosmic evolution are fundamentally incomplete. Some unknown force or field must be operating on scales larger than anything scientists have previously considered, capable of correlating galaxy spins across distances so vast that light requires hundreds of millions of years to cross them. A rotating universe would have different physical properties than the static, isotropic cosmos described by standard models. Space-time itself might have preferred directions, creating asymmetries and physical laws that could affect everything from particle physics to the ultimate fate of cosmic expansion. The implications extend to dark energy, the mysterious force driving accelerating expansion. If the universe has a preferred rotational axis, dark energy's effects might vary depending on direction, creating a cosmos that expands faster in some orientations than others. Perhaps most unsettling is what a rotating universe suggests about our place in the cosmic hierarchy. If our universe is spinning inside a larger structure, it implies that reality extends far beyond the observable cosmos. We might be living inside just one component of an incomprehensibly vast multiverse, where entire universes rotate like galaxies within some higher dimensional space. The coordinated galaxy rotations represent a fundamental challenge to the cosmological principle, the assumption that the universe looks roughly the same from any vantage point. This principle has guided cosmology for decades, simplifying the mathematics of cosmic models and allowing scientists to extrapolate local observations to universal conclusions. If the principle is wrong, if the universe has large-scale structure and preferred directions that violate isotropy, then every cosmological calculation based on this assumption might be systematically biased. Webb's discovery of coordinated spins adds to mounting evidence that the universe is more structured, more complex, and more asymmetric than our models predict. The telescope has found giant cosmic voids, massive galaxy superclusters, and large-scale velocity flows that all push against the limits of what standard cosmology comfortably allows. Each new observation reveals that the cosmos operates according to rules more subtle and more strange than our equations capture. But the strangest discoveries were still emerging from Webb's surveys of the cosmic deep, where the telescope was finding objects that do not fit into any known category of astronomical phenomena. Webb has identified over 300 mysterious objects glowing in the early universe that astronomers call little red dots. These appear as tiny crimson pinpricks scattered throughout images of cosmic dawn, each one far brighter than it should be given what we know about galaxy and star formation in the universe's youth. The objects show properties so unusual that scientists cannot classify them. The mystery begins with their extreme luminosity. These are not faint, distant galaxies struggling to form their first stars. They are blazing beacons producing enormous amounts of energy through unknown processes. Some appear point-like, suggesting they might be powered by supermassive black holes rather than distributed star formation. Others show evidence of extended structure, indicating they could be genuine galaxies undergoing extraordinarily rapid stellar birth. Bang Jiang's son, a graduate student at the University of Missouri, led the team that systematically identified 300 of these enigmatic objects in Webb's deep field data. Each one exists when the universe was less than 1 billion years old, yet produces light equivalent to mature galaxies containing hundreds of billions of stars. Traditional galaxy formation models cannot explain such extreme luminosity at these early epochs. The most disturbing possibility is that these objects represent a completely unknown phase of cosmic evolution. During the universe's first billion years, physical conditions were drastically different from today. Matter was denser. The cosmic microwave background radiation was hotter. Dark matter interactions were more frequent. The cosmic web of large-scale structure was still forming. Perhaps these extreme conditions allowed for types of object formation that cannot happen in the modern universe. Some little red dots show evidence of extremely high-energy processes. They emit X-rays, ultraviolet radiation, and infrared light in patterns suggesting violent, chaotic energy production. Whatever is powering these objects operates under extreme conditions that push the boundaries of known physics. The emissions indicate temperatures exceeding millions of Kelvin, magnetic field strengths billions of times stronger than Earth's, and matter acceleration to relativistic velocities. The objects also appear distributed randomly throughout space, rather than clustered in regions where early galaxy formation was expected. This random distribution suggests they might represent a fundamental property of the early universe, rather than rare, isolated phenomena. If little red dots are common features of cosmic dawn, then our understanding of how structure formed during the universe's youth is fundamentally incomplete. The little red dots represent perhaps the most significant challenge to cosmology that Webb has discovered. Even if only a few of these objects are confirmed to exist in the early universe with the properties initial observations suggest, they will force scientists to modify existing theories of galaxy formation, black hole growth, and cosmic structure formation. If hundreds exist, as Webb surveys indicate, then the standard model of cosmology faces a crisis that might require fundamentally new physics to resolve. But the little red dots were just one class of mysterious object Webb was discovering in the cosmic deep. The telescope's surveys were revealing layer after layer of unexpected phenomena, each more difficult to explain than the last. 6 massive galaxies, designated as sleeping beauties, sit dormant in regions of space, where they should be blazing with star formation. Webb discovered these cosmic giants scattered throughout the early universe, massive star systems containing billions of stars, but showing no signs of creating new ones. They defy every model of how galaxies evolved during their youth. The discovery emerged when astronomers examined galaxies that formed between 600 million and 6 billion years after the Big Bang. During this period, the universe was rich with gas and dark matter, creating ideal conditions for rapid star formation. Most galaxies from this era should be consuming available gas at furious rates, building their stellar populations through vigorous star birth. Instead, Webb found numerous massive galaxies that appear to have fallen into cosmic hibernation. These systems contain stellar masses comparable to our Milky Way, but show none of the active star formation expected from young galaxies. Their spectra reveal old stellar populations dominated by red giant stars, indicating that star formation shut down hundreds of millions or even billions of years before the observations. It is like finding massive cities where all construction suddenly stopped for no apparent reason. Several theories attempt to explain this bizarre behavior, and each challenges fundamental assumptions about galaxy evolution. First, supermassive black holes at the centers of these galaxies became so active that their energy output heated surrounding gas to temperatures too hot for star formation. This process, called active galactic nucleus feedback, can shut down star formation across entire galaxies when jets and winds from accreting black holes inject enormous energy into the interstellar medium. But the timing does not match. The Sleeping Beauty galaxies show signs of having shut down their star formation before their central black holes became active enough to cause such widespread heating. Something else must have triggered their dormancy. A second theory proposes that these galaxies consumed their gas supply so rapidly during an initial burst of star formation that they literally ran out of fuel. This explanation requires star formation rates far higher than current models predict, suggesting early galaxies could build stars much more efficiently than modern systems. If true, it implies that the physics of star formation operates differently under the high-density conditions of the early universe. The most disturbing possibility is that the Sleeping Beauty galaxies encountered some unknown process that does not exist in the modern universe. The early cosmos operated under different physical conditions, with higher matter densities, stronger radiation fields, and different dark matter distributions. Perhaps these conditions allowed for star formation shutdown mechanisms we have never observed, processes that could quench galaxy growth through pathways that no longer exist in today's low-density cosmic environment. The existence of dormant galaxies in the early universe has profound implications for our understanding of cosmic evolution. If massive galaxies could shut down their growth processes so early in cosmic history, it suggests galaxy formation is far more complex and unpredictable than scientists previously believed. The Sleeping Beauties represent evidence that the early universe was capable of creating mature, evolved systems far faster than our models allow, then shutting them down through mechanisms we cannot identify. These cosmic mysteries were accumulating faster than theories could explain them. Every deep-field image Webb captured revealed new classes of impossible objects. Every spectroscopic analysis uncovered unexpected chemical compositions. Every survey of distant structure found patterns that violated predictions. The universe was not behaving according to the rules we thought governed its evolution. But the most disturbing discoveries were still emerging from Webb's examination of extreme environments, where physics operates at the boundary between classical and quantum regimes. Deep in a colliding galaxy system astronomers nicknamed the Infinity Galaxy, Webb discovered a supermassive black hole forming through direct gravitational collapse. The system displays 2 compact red nuclei surrounded by glowing rings, creating a perfect figure-8 pattern. Between these nuclei, suspended in a vast expanse of glowing hydrogen gas, sits a monster containing 50 million solar masses. This positioning should be gravitationally unstable. The black hole should be pulled toward one nucleus or the other, not floating in the middle like a cosmic referee. Peter van Dokkum and Gabriel Brammer discovered this system while examining Webb's deep-field images. The galaxy's distinctive shape immediately caught their attention, but follow-up observations revealed something far more significant. Radio emissions pinpoint a massive black hole exactly where theory says it should not survive. The direct collapse process works like a cosmic avalanche. When two galaxies crashed together, they created enormous streams of gas flowing between their cores. Under exactly the right conditions, these gas streams became so massive and dense that they collapsed directly into a black hole without ever forming stars. It is gravitational collapse without the intermediate step of stellar evolution. This discovery solves one of Webb's most puzzling findings. The telescope has found supermassive black holes throughout the early universe that are far too massive for their age. Traditional black hole formation requires waiting for massive stars to form, evolve, and die in supernova explosions. That process takes hundreds of millions of years minimum, but Webb has found mature, supermassive black holes existing just 600 million years after the Big Bang, containing tens of millions or even hundreds of millions of solar masses. Direct collapse black holes can reach supermassive status much more quickly because they start with enormous amounts of material. Instead of beginning as stellar mass black holes weighing perhaps 10 or 20 solar masses and growing through accretion, they form with masses potentially millions of times greater. This head start allows them to become the monsters Webb observes in the early universe. The Infinity Galaxy represents a real-time laboratory for studying this exotic formation process. The black hole is actively feeding on gas flowing between the colliding galactic cores, growing larger as astronomers watch. Radio observations show intense energy emissions from exactly where the black hole should be located, confirming it is actively consuming matter and converting gravitational potential energy into radiation across the electromagnetic spectrum. But the direct collapse mechanism raises disturbing questions about cosmic violence during the universe's youth. If such processes were common in the early cosmos, it means galaxy formation was accompanied by catastrophic events that could instantly create some of the most massive objects in the universe. The collisions required to trigger direct collapse would have been extraordinarily energetic, releasing energies equivalent to billions of supernovae, sterilizing vast regions of space with radiation and shockwaves. The process also suggests supermassive black holes might be more fundamental to cosmic structure than previously thought. Instead of forming as byproducts of galaxy evolution, they might be primary drivers of how matter organizes on the largest scales. The gravitational wells created by direct collapse black holes could serve as seeds around which galaxies assembled, inverting our understanding of the relationship between black holes and their host galaxies. But even direct collapse could not explain the most extreme feeding behavior Webb was about to discover lurking in the cosmic deep. Hidden among thousands of X-ray sources, Webb identified a supermassive black hole consuming matter at 40 times its theoretical limit. The object designated LID 568 is devouring material at rates that physics says should be impossible. Every black hole has an Eddington limit, the maximum rate at which it can accrete matter without the intense radiation pressure from superheated gases blowing away its food supply. LID 568 violates this limit by a factor of 40. It is drinking from 40 fire hoses simultaneously. The discovery required combining Webb's infrared sensitivity with data from NASA's Chandra X-ray Observatory. LID 568 was initially buried among thousands of bright X-ray sources, invisible to optical telescopes but blazing in high-energy radiation. Webb's unique infrared capabilities allowed astronomers to identify the faint counterpart emissions that revealed the object's true nature and distance. What makes this black hole's feeding frenzy truly disturbing is the implications for its growth rate. At such extreme accretion rates, LID 568 could have gained most of its current mass in a single episode of rapid feeding. The black hole appears to be undergoing a super Eddington accretion event, consuming enormous amounts of matter in a relatively brief cosmic time span measured in millions rather than billions of years. The object exists just 1.5 billion years after the Big Bang, an epoch when the universe was still in its infancy. For a black hole to reach supermassive status so quickly, while respecting normal feeding limits, would require starting from impossibly large seed masses. LID 568's extreme feeding rate provides a potential solution to this timing problem. If black holes can undergo periodic super-Eddington accretion events, they could grow from stellar mass seeds to supermassive status far faster than standard models predict. The physics of such extreme feeding remains poorly understood. The black hole is somehow stabilizing the accretion process, despite radiation pressures that should blow away its food supply. Either the black hole has developed mechanisms for controlling radiation pressure through magnetic fields or geometric effects, or the surrounding matter has properties that allow it to resist being blown away. Some models suggest that super-Eddington accretion might occur when matter falls into the black hole in dense clumps rather than smoothly, allowing some material to shield other material from radiation pressure. LID 568 represents the extreme end of black hole feeding behavior, operating under conditions that push physics to its breaking point. The discovery suggests the early universe hosted feeding events far more violent and rapid than anything seen in the modern cosmos. These fast-feeding monsters could explain how supermassive black holes reached their enormous sizes so quickly in cosmic history, through brief but intense episodes, rather than slow, steady growth over billions of years. But the mysteries of black hole growth were just one aspect of the cosmic violence Webb was documenting throughout the early universe. An ancient comet from another star system is racing through our solar system, and it is older than Earth, the Sun, and everything we call home. Comet 3I/Atlas appears unremarkable at first glance. It measures approximately 7 miles wide, composed of ice and rock, following a trajectory that will take it past our Sun before returning to the void between stars. But Webb's detailed analysis revealed something that should not be possible. This interstellar visitor is approximately 7 billion years old, making it 3 billion years older than our entire solar system. When astronomers tracked the comet's trajectory through space, they realized it came from the Milky Way's thick disk, a region filled with ancient stars that formed when the universe was much younger. This cosmic wanderer has been drifting through interstellar space since before the Sun was even a glimmer in a stellar nursery. It predates Earth, Mars, Jupiter, and every planet in our neighborhood by billions of years. Webb's near-infrared spectrograph revealed that the comet's coma, the cloud of gas and dust surrounding its nucleus, is dominated by carbon dioxide rather than the water vapor typical of comets from our solar system. This unusual composition provides clues about the chemical environment of the star system, where it formed 7 billion years ago. When the Milky Way was more chaotic and violent, star formation rates were higher and heavy elements were scarcer. The comet is traveling at over 130,000 miles per hour, fast enough to cross the entire United States in less than 2 minutes. Its trajectory is unusually flat and straight, unlike anything else in our solar system. This interstellar intruder follows the gravitational rules of the galaxy rather than our Sun, treating our entire solar system as just another obstacle to navigate around. What makes this ancient visitor truly unsettling is what it represents. 3I/Atlas is a messenger from a time when the universe was radically different. 7 billion years ago, the Milky Way was more turbulent. Star formation was more vigorous. Chemical processes operated under different conditions. This comet formed around a star that lived and died billions of years before our Sun existed. It survived the death of its parent star, possibly a violent supernova explosion that destroyed its original solar system and sent it wandering through the galaxy. For 3 billion years, it traveled through the cosmic deep, a frozen time capsule carrying chemical signatures from an ancient epoch. The fact that we are seeing it now raises disturbing questions about how many other ancient visitors might be passing through our solar system undetected. 3I/Atlas is only the third confirmed interstellar object ever discovered, but statistical models suggest dozens or hundreds of these cosmic time travelers should be crossing our neighborhood at any given moment. Each represents a fragment of a destroyed world, a piece of cosmic history that survived catastrophes we can barely imagine. They are archaeological artifacts from stellar systems that existed when the universe was young, carrying information about galactic conditions from epochs that no other objects can provide. But 3I/Atlas also serves as a reminder of our solar system's ultimate fate. In a few billion years, when our Sun begins to die, objects from our world might be ejected into interstellar space, becoming ancient wanderers that will puzzle astronomers in distant galaxies long after Earth is gone. The ancient comet's visit was just one example of the cosmic timescales that dwarf human understanding. But Webb's surveys were revealing objects even more mysterious than visitors from dead star systems. A rogue planet drifting through space has developed the most bizarre atmosphere ever discovered, with separate cloud layers made of iron and magnesium minerals. SIMP J01365663 plus 0933473 is unlike any world in our solar system. This cosmic wanderer does not orbit a star, but instead drifts freely through the galaxy, illuminated only by the faint glow of its own internal heat. Webb's detailed atmospheric analysis revealed something unprecedented. This rogue planet has a layered atmosphere where iron rain falls through clouds made of magnesium silicates. The planet's atmosphere resembles a cosmic layer cake, with different types of metallic clouds stacked at various altitudes, creating weather systems unlike anything on Earth. Near the surface, dense layers of iron clouds create weather patterns beyond terrestrial experience. These are not wisps of water vapor, but thick concentrations of vaporized metal that condense and fall as liquid iron rain during the planet's storms. The droplets would be hot enough to melt rock, falling through an atmosphere composed primarily of hydrogen and helium, creating a scene of apocalyptic metallurgical violence. Higher in the atmosphere, a second cloud layer composed of forsterite, a magnesium-rich mineral commonly found in meteorites, creates an entirely different weather system. These silicate clouds form when temperatures and pressures reach exactly the right conditions for magnesium compounds to vaporize and condense. The mineral exists on Earth primarily in the mantles of terrestrial planets and in meteorites, material forged in stellar explosions and planetary collisions. The interaction between these two cloud layers creates atmospheric dynamics that push the boundaries of planetary science. Webb's infrared observations revealed that both cloud layers are patchy and constantly changing, suggesting active weather patterns driven by the planet's rotation and internal heat sources. The iron clouds appear to follow different circulation patterns than the magnesium clouds, creating a complex three-dimensional atmospheric structure that varies dramatically across the planet's surface. But the most mysterious aspect of this world's atmosphere comes from high above both cloud layers, where Webb detected what researchers call hotspots. These are regions of intense heat that appear to be powered by radio auroras, electromagnetic phenomena similar to Earth's northern lights, but operating at energy levels that would be lethal to any known form of life. The radio auroras suggest SIMP J01365663 plus 0933473 has an incredibly powerful magnetic field, far stronger than anything in our solar system. This magnetic field interacts with charged particles in interstellar space, creating electrical currents that heat portions of the upper atmosphere to temperatures exceeding those found in the metallic cloud layers below. Alison McCarthy, the graduate student leading the atmospheric analysis, described the planet as having variability mechanisms that had been hypothesized but never directly observed. The complex interactions between iron clouds, magnesium clouds, and radio auroras create an atmospheric system operating according to principles we have never encountered before. The existence of such complex atmospheric chemistry on a rogue planet raises disturbing questions about planetary formation and evolution. SIMP J01365663 plus 0933473 somehow developed and maintained this elaborate atmosphere while drifting through the cold emptiness of interstellar space, far from any stellar energy source. This suggests rogue planets might be capable of supporting much more complex atmospheric processes than scientists previously imagined. If one wandering world can develop iron rain and magnesium clouds, there could be millions of similar objects throughout the galaxy, each hosting unique atmospheric phenomena we have never considered possible. The metallic rain world represents a new category of planetary atmosphere that challenges our understanding of what kinds of weather systems can exist in the universe. But atmospheric discoveries were just one class of impossible observation Webb was accumulating. The telescope's surveys were revealing that the universe operates according to rules far stranger than our models predict. Magnetic fields discovered throughout the cosmic web are as complex as human brain networks, and they are older than any known structure in the universe. Webb has detected evidence of magnetic fields stretching across the largest structures in the cosmos, creating patterns of connectivity that eerily resemble the neural networks found in biological brains. These primordial magnetic fields appear to be remnants from the universe's first billion years, when cosmic structure was still forming through processes we barely understand. The discovery emerged from Webb's observations of the cosmic web, the vast network of filaments and voids that organizes matter on the largest scales. Between galaxies and galaxy clusters, thin streams of gas and dark matter create bridges spanning hundreds of millions of light-years. Webb found that these cosmic filaments are threaded with magnetic fields of extraordinary complexity. The magnetic field patterns show a level of organization that should not exist in the early universe. Instead of simple, uniform fields, Webb detected intricate networks with nodes, connections, and hierarchical structures that mirror the topology of biological neural networks. The similarity is so striking that researchers are using the same mathematical tools developed to study brain connectivity to analyze cosmic magnetism. These ancient magnetic fields raise fundamental questions about cosmic evolution. Standard models assume magnetic fields in space develop gradually as galaxies and stars form, with stellar winds and supernova explosions creating and amplifying magnetic structures over billions of years. The primordial fields Webb discovered appear to predate this process entirely, existing before the first stars ignited. The fields show evidence of having influenced early galaxy formation in ways current theories do not account for. Magnetic pressure and magnetic reconnection events might have shaped how gas collapsed into the first stars, affecting stellar masses, formation rates, and the chemical evolution of early galaxies. If primordial magnetism was stronger and more organized than models assume, it could explain some of the anomalies Webb has found in early cosmic structure. Perhaps most disturbing is what these magnetic networks suggest about the nature of cosmic structure formation. The brain-like patterns indicate the universe developed organizational complexity far earlier than scientists believed possible. Instead of simple gravitational collapse creating cosmic structure, the early cosmos might have operated more like a vast information processing system, with magnetic fields serving as communication channels connecting different regions of space. The magnetic field networks also appear dynamic, with connections forming and breaking across cosmic time. Webb detected evidence of magnetic storms spanning entire galaxy clusters, events that could affect star formation and galactic evolution across vast regions of space. These storms release energies equivalent to billions of supernovae, restructuring magnetic topologies and driving turbulence in the intergalactic medium. The discovery has implications for our understanding of dark matter and dark energy. Magnetic fields can interact with charged particles in ways that affect how matter clumps together on large scales. If primordial magnetism was more complex and powerful than current models assume, it might explain some of the discrepancies Webb has found in cosmic structure formation, including the universe breakers and the coordinated galaxy rotations. The brain-like magnetic networks represent a fundamental challenge to our understanding of how complexity emerges in the universe. If such sophisticated organizational structures existed in the cosmic web's youth, it suggests the universe has intrinsic tendencies toward complexity that we have never recognized. These primordial magnetic fields might be evidence that the cosmos itself has properties analogous to living systems, with information processing and organizational capabilities that emerge from physical processes we do not yet understand. But the magnetic discoveries were just one aspect of the large-scale structure anomalies Webb was documenting. The telescope's surveys were revealing that the universe's evolution has been far more violent and chaotic than our models predict. Invisible forces are reshaping cosmic structure through violent processes that leave galaxies shredded and scattered across millions of light-years. Webb has uncovered evidence that dark matter, the mysterious substance comprising 85% of all matter in the universe, participates in violent interactions that can tear apart entire galaxies. The evidence comes from Webb's observations of galaxy clusters, regions where hundreds of galaxies are held together by the gravitational influence of massive dark matter concentrations. When these cosmic cities collide, they create some of the most energetic events in the universe, releasing energies comparable to billions of supernova explosions. But Webb's detailed imaging revealed that the violence extends far beyond the visible collision zones. Galaxies located millions of light-years from cluster collisions show signs of having been violently disrupted by gravitational forces that can only be explained by dark matter interactions operating on previously unimaginable scales. The telescope detected extensive streams of stars and gas connecting galaxies across vast distances, creating bridge-like structures that span the space between separate galactic systems. These stellar streams represent the torn remnants of galaxies that have been gravitationally shredded by dark matter forces during cluster interactions. What makes this cosmic violence particularly disturbing is its hidden nature. While normal matter interactions create visible fireworks through electromagnetic radiation, dark matter collisions produce no light, no heat, and no electromagnetic signatures. The only evidence of these catastrophic events comes from their gravitational effects on the matter we can see. Webb's infrared sensitivity has revealed the full extent of this dark violence. Faint stellar streams and tidal tails extend for millions of light-years around galaxy clusters, creating vast spiderwebs of disrupted matter that previous telescopes were too insensitive to detect. Each stream represents a galaxy that has been partially or completely destroyed by dark matter interactions, its stars scattered across intergalactic space like debris from a cosmic shipwreck. The scale of this destruction suggests dark matter does not simply provide passive gravitational scaffolding for cosmic structure. Instead, it participates actively in reshaping the universe through violent processes that can eject galaxies from their host clusters, strip away their gas supplies, and scatter their stars across intergalactic space. Computer simulations of dark matter interactions show these violent events might be fundamental to cosmic evolution. Dark matter particles can undergo collisions and gravitational interactions that create shockwaves propagating through the cosmic web, affecting galaxy formation across vast regions. These shocks heat the intergalactic medium, trigger star formation bursts, and disrupt galactic structures in ways that ordinary matter alone cannot achieve. Perhaps most unsettling is what this hidden violence suggests about the nature of dark matter itself. If dark matter can participate in such energetic interactions, it might have properties beyond simple gravitational attraction. Some models propose that dark matter particles can undergo phase transitions or interact through forces we have not yet identified, forces that become important only under the extreme densities found in cluster collisions. The discovery of widespread dark matter violence also affects our understanding of galaxy evolution and the formation of cosmic structure. If galaxies are constantly being disrupted and reformed through dark matter interactions, the universe might be far more dynamic and chaotic than our models predict. The smooth, gradual evolution described in cosmology textbooks might be an idealization that misses the violent reality of how structure actually forms and evolves. These invisible catastrophes represent a fundamental aspect of cosmic evolution that operates completely outside our direct observation, shaping the universe through violence we can only detect through its aftermath. Dark matter is not the invisible scaffold we thought it was. It is an active participant in cosmic violence, tearing galaxies apart through mechanisms we are only beginning to understand. The accumulating weight of Webb's discoveries was forcing a fundamental re-evaluation of cosmology. Every major prediction of the Standard Model was being challenged by observations that revealed a universe operating according to rules we never anticipated. The expansion crisis. The impossible early galaxies, the supermassive black holes that should not exist. The coordinated galaxy spins, the mysterious little red dots. Each observation added to a growing pile of evidence suggesting our cosmic models are fundamentally incomplete. But perhaps the most disturbing possibility was emerging from the pattern of anomalies itself. The coordinated galaxy rotations, the strange behavior of cosmic expansion, the primordial black holes. Together, these observations pointed toward a conclusion so radical it threatened to overturn our entire understanding of reality. We might be living inside a black hole within a larger universe. The evidence begins with the galaxy rotation patterns Webb discovered during its deep surveys. Galaxies separated by millions of light-years are spinning in coordinated directions, a phenomenon that should be impossible unless the entire universe has a preferred rotational axis. In black hole cosmology, this coordination would result from our universe inheriting the angular momentum of the parent black hole that contains us. The theory suggests that what we call the Big Bang was actually our universe crossing the event horizon of a massive black hole in a higher dimensional space. From our perspective inside the black hole, this crossing appears as cosmic expansion. But from the perspective of the larger universe, we are falling toward the black hole singularity in a process that will take infinite time due to gravitational time dilation. This scenario explains the accelerating expansion of space that we attribute to dark energy. As we fall deeper into the parent black hole, space-time curvature increases, creating the illusion that expansion is accelerating when we are actually approaching regions of more severe gravitational distortion. The expansion is not driven by a mysterious dark energy component. It is the geometric consequence of our motion through increasingly curved spacetime. Webb's discovery of primordial black holes that predate star formation also fits the black hole cosmology model. These ancient monsters could be smaller black holes that existed in the parent universe before we crossed the event horizon, appearing in our cosmic history as primordial objects that formed before normal matter could collapse into stars. They would be relics from the larger universe, immigrants that crossed the event horizon with us and became embedded in our spacetime. The coordinated galaxy spins that Webb observed across vast regions of space make perfect sense if our universe inherited rotational momentum from a spinning parent black hole. The galaxies are not mysteriously coordinating their motion. They are all participating in the same cosmic rotation that was imprinted on spacetime when our universe formed. Every structure that condenses from the cosmic expansion would naturally inherit this rotational bias, creating the patterns Webb detected. Even the expansion rate contradictions that have puzzled astronomers fit the black hole cosmology model. Different measurement techniques might be detecting different aspects of our motion through the curved spacetime inside the parent black hole, creating apparent contradictions that result from viewing the same phenomenon from multiple perspectives. The Hubble tension is not a crisis in cosmology. It is evidence that we are measuring motion through a gravitational field rather than simple expansion of flat space. If black hole cosmology is correct, it means everything we can observe, from the cosmic microwave background to the most distant galaxies, exists within the event horizon of an incomprehensibly massive black hole. We would be forever separated from the larger universe that contains us, unable to communicate with or affect anything outside our cosmic prison. Every signal we send, every exploration we attempt, will remain trapped within the event horizon, doomed to eventually fall toward the singularity we can never reach. The theory also suggests that black holes throughout our universe might contain entire universes of their own, creating a nested hierarchy of cosmic structures where each black hole serves as a gateway to a complete cosmic realm with its own physics, evolution, and potentially life. Every stellar mass black hole might contain a miniature universe. Every supermassive black hole might host a cosmos as vast and complex as our own. This possibility transforms our understanding of cosmic significance and our place in the broader structure of reality. What we call the universe might be just one bubble in an infinite multiverse of black hole universes, each isolated from all others by impenetrable event horizons. The concept of the universe becomes meaningless. There are only universes, plural, nested within each other like Russian dolls extending infinitely in both directions. The implications extend to fundamental physics. If we live inside a black hole, the laws of physics we observe might be emergent properties of the event horizon, rather than fundamental laws governing all of reality. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary, takes on new meaning. Our three-dimensional universe might be a holographic projection from information encoded on the event horizon that surrounds us. Quantum mechanics and general relativity might be reconciled not through string theory or loop quantum gravity, but through understanding how information behaves at event horizons. The measurement problem in quantum mechanics, the black hole information paradox, and the nature of space-time singularities might all find solutions in a framework that treats our universe as the interior of a black hole. But accepting black hole cosmology requires confronting profoundly disturbing implications about free will, causality, and the nature of time itself. Inside a black hole event horizon, all time-like paths lead inevitably toward the singularity. You cannot stop moving forward in time toward the singularity, any more than you can stop moving forward in time generally. If we live inside a black hole, the universe's ultimate fate is not heat death or big rip or vacuum decay. It is collision with the singularity at the end of time. Every galaxy, every star, every atom will eventually reach this singularity. The journey might take googles of years from our perspective, stretched by time dilation to durations that make the current age of the universe seem like a quantum fluctuation. But the destination is inevitable. We are all falling toward the same point, unable to escape, unable to reverse course, following trajectories determined the moment we crossed the event horizon. This raises the question of whether free will exists at all. If our universe's entire history from Big Bang to final singularity is just the interior geometry of a black hole that formed in a larger universe, then everything that will ever happen might be determined by the initial conditions when the black hole formed. Every choice you make, every thought you have, might be part of a predetermined trajectory through spacetime that was set 13.8 billion years ago. The cosmic microwave background would be the last light to enter the black hole before the event horizon closed. Its temperature fluctuations would encode the final state of the collapsing matter in the parent universe, frozen in time at the moment of horizon formation. When we measure these fluctuations with instruments like Planck and Webb, we are examining the boundary conditions of our cosmic prison. The accelerating expansion we observe might be approaching relativistic speeds as we fall toward the singularity. Time dilation effects could become extreme in the far future, making the final moments before singularity impact stretch to infinite duration from our perspective. The universe might never actually end from the viewpoint of internal observers, asymptotically approaching but never reaching the singularity, experiencing eternal expansion into darkness. Webb's discovery of quantum foam breaches and space-time instabilities takes on new significance in black hole cosmology. These phenomena might be evidence that we are approaching regions of extreme space-time curvature where classical general relativity breaks down. The closer we fall toward the singularity, the more frequently quantum gravitational effects will intrude into our macroscopic reality. The strange objects Webb discovered, the universe breakers, the impossible early galaxies, the primordial black holes, might all be artifacts of living in this exotic space-time geometry. Physical processes near an event horizon operate under conditions that do not exist in flat spacetime. Hawking radiation, frame dragging, and gravitational time dilation create environments where standard physics gives unexpected results. If this is true, then every cosmological mystery Webb has uncovered might trace back to a single root cause. We are not observing a universe evolving according to lambda cold dark matter cosmology in flat or gently curved spacetime. We are observing the interior of a black hole, where spacetime curvature is extreme, where quantum effects scale to cosmic dimensions, where the rules we derived from local physics experiments break down. But black hole cosmology faces serious challenges. The cosmic microwave background shows a level of isotropy and homogeneity difficult to explain if we live in a rotating black hole. The temperature fluctuations are incredibly small, only 1 part in 100,000, suggesting the early universe was extraordinarily uniform. A rotating black hole interior should show stronger asymmetries. Proponents argue that the black hole might be so massive, and we might be so far from the singularity, that local spacetime appears nearly flat and isotropic. Just as Earth's surface appears flat from ground level despite being a sphere, the black hole interior might appear homogeneous despite being part of a highly curved structure. The deviations from perfect isotropy that Webb is detecting, like the coordinated galaxy spins, might be our first glimpses of the underlying curvature. The theory also struggles to explain how matter and energy could have been so evenly distributed at the moment of event horizon crossing. Standard Big Bang cosmology invokes inflation, a period of exponential expansion in the first fraction of a second, to explain cosmic homogeneity. Black hole cosmology would need a different mechanism, perhaps related to the dynamics of gravitational collapse in the parent universe. Some researchers propose that the collapsing matter in the parent universe underwent a period of extreme compression and mixing before forming the black hole, creating the homogeneous initial conditions we observe. Others suggest that quantum effects near the forming event horizon could have erased inhomogeneities through processes we do not yet understand. Regardless of whether black hole cosmology is correct, Webb's discoveries have revealed that the universe operates according to principles stranger than our models capture. The telescope has documented phenomena at every scale, from planetary atmospheres to cosmic structure, that defy conventional explanation. Each observation adds to the weight of evidence, suggesting our understanding of reality is incomplete. The void looked back, and what it revealed challenges everything we thought we knew. Beyond the theoretical implications, Webb's observations have practical consequences for our cosmic future. If we live inside a black hole, there are fundamental limits to how far we can explore and how much of reality we can access. The parent universe beyond our event horizon is forever unreachable. Any civilization that arose in our universe faces the same constraints. We are all prisoners in the same cosmic cell. This has implications for the Fermi paradox, the question of why we have not detected evidence of extraterrestrial civilizations, despite the apparent high probability they should exist. If we are inside a black hole universe, then all civilizations that could ever arise are confined to the same region of space-time. The galaxy might be teeming with intelligent species, all trapped in the same black hole, none capable of escaping to the larger universe. The ultimate fate of any civilization becomes irrelevant on cosmic timescales. Whether we colonize the galaxy, upload our consciousness to machines, or destroy ourselves, the endpoint is the same. All matter and information will eventually fall into the singularity. Every accomplishment, every work of art, every thought ever conceived will be compressed to infinite density and possibly annihilated. Some physicists speculate that information might somehow survive singularity collision, perhaps being radiated back out through Hawking radiation or being preserved in the geometry of space-time itself. But these are speculations without firm theoretical foundation or experimental evidence. The singularity theorems of general relativity suggest that matter and information reaching a singularity cease to exist in any meaningful sense. This is the ultimate cosmic horror. Not heat death, where the universe fades slowly into cold darkness over googles of years. Not vacuum decay, where quantum tunneling suddenly destroys space-time. But inevitable collision with a singularity where the laws of physics break down completely, where matter, energy, space, and time lose all meaning. Webb has given us glimpses into this abyss. The telescope's observations reveal a universe far stranger, more violent, and more mysterious than we imagined. Every deep-field image contains objects that should not exist. Every spectrum shows chemical compositions that defy explanation. Every measurement of cosmic structure reveals patterns that violate our models. The coordinated galaxy rotations suggest the universe has memory, that it was born with properties imprinted at its creation. The primordial black holes suggest monsters older than stars have been lurking in the darkness since the beginning. The impossible early galaxies suggest the universe achieved complexity far faster than physics allows. The expansion contradictions suggest space-time itself is unstable, changing properties as we probe deeper. These are not isolated anomalies that can be explained away with small modifications to existing theory. They are systematic violations of our cosmological framework, occurring across multiple independent observations and measurement techniques. The universe is telling us something fundamental about its nature, and we are only beginning to decode the message. But perhaps the most disturbing aspect of Webb's discoveries is what they reveal about scientific epistemology. For decades, we believed we understood the universe's basic properties. We measured the Hubble constant. We mapped the cosmic microwave background. We tracked supernova explosions. We built a standard model of cosmology that explained observations with remarkable precision. Webb has revealed that this precision was illusory. We were not measuring fundamental properties of the universe. We were measuring local conditions in a tiny patch of spacetime, then extrapolating those measurements to cosmic scales where they do not apply. We assumed the universe was simple, homogeneous, governed by a small set of physical laws operating uniformly across space and time. The universe is not simple. It is baroque, complex, filled with structures and processes, operating on scales and under conditions we cannot reproduce in laboratories. The laws of physics we derive from terrestrial experiments might be local approximations that break down under extreme cosmic conditions. Quantum mechanics and general relativity might both be wrong, not in the regimes we have tested them, but in the vast unexplored parameter spaces of the deep universe. This epistemological crisis extends beyond cosmology to fundamental physics. The standard model of particle physics has been remarkably successful, explaining thousands of experiments with extraordinary precision. But it is incomplete. It cannot explain dark matter, dark energy, or the matter-antimatter asymmetry. It predicts a cosmological constant 120 orders of magnitude larger than observed. These are not small discrepancies. They are failures so extreme, they suggest we are missing fundamental physics. Webb's discoveries in cosmology parallel the mysteries in particle physics. Both domains reveal that our models work well in limited regimes, but fail catastrophically when extrapolated beyond those regimes. The universe might be fundamentally unknowable in its totality. We can understand local physics, derive equations that describe phenomena in our laboratory, our solar system, perhaps even our galaxy. But the deep universe, the cosmic structure on the largest scales, the physics operating under extreme conditions of density and curvature, might be forever beyond our grasp. This is not due to technological limitations. It is due to fundamental barriers in how information propagates through space-time. Light speed is finite. Event horizons exist. Quantum mechanics limits the precision of simultaneous measurements. These are not engineering challenges to overcome with better instruments. They are hard limits imposed by the structure of reality itself. Webb represents perhaps the ultimate astronomical instrument humanity will build in the foreseeable future. Its mirror is near the theoretical maximum size that can be launched and deployed in space. Its instruments operate at the edge of quantum noise limits. Its orbit at the Lagrange point provides the stable thermal environment necessary for infrared observations. Future telescopes might be larger or more sensitive, but they will face the same fundamental limits. We have reached a point where the universe's secrets are protected not by our technological limitations, but by the laws of physics themselves. The observations Webb has made, the impossible galaxies and primordial black holes and coordinated spins, might be as close as we ever get to understanding the true nature of cosmic structure. And that might be the void's final message: not answers but questions, not understanding but mystery. The universe does not owe us comprehensibility. It exists according to its own logic, following principles that might be fundamentally alien to human cognition. Our brains evolved to hunt antelope on African savannas, to recognize faces, to model social dynamics. We are adapted for survival in Earth's environment, not for understanding quantum mechanics or cosmology. The fact that we can comprehend anything about the universe is remarkable. The fact that we cannot comprehend everything should not surprise us. Webb has revealed the limits of human knowledge. The telescope has shown us wonders beyond imagination and horrors beyond description. It has documented a universe more complex, more violent, and more strange than our ancestors could have conceived. And in doing so, it has revealed how little we truly understand. The void looked back. And it asked questions we cannot answer. But understanding might not be the point. Perhaps the value of Webb's discoveries lies not in explaining the universe, but in revealing how much remains unexplained. Each observation that defies our models is an opportunity to expand our conceptual frameworks, to imagine new physics, to venture beyond the comfortable certainties of established theory. The universe breakers force us to reconsider galaxy formation. Maybe dark matter clumps more efficiently in the early universe. Maybe star formation proceeded through mechanisms that do not exist today. Maybe the initial density fluctuations after the Big Bang had more power on small scales than inflation models predict. The primordial black holes force us to reconsider cosmic structure formation. Maybe black holes are fundamental building blocks rather than byproducts. Maybe they seeded galaxy formation rather than growing within galaxies. Maybe the universe's large-scale structure is determined more by black hole dynamics than by dark matter gravitational collapse. The expansion contradictions force us to reconsider dark energy. Maybe it evolves over time. Maybe it has spatial variation. Maybe it is not a cosmological constant, but a dynamic field that changes properties as the universe ages. Maybe general relativity needs modification on cosmological scales. Each mystery Webb uncovers becomes a research program for the next generation of scientists. The telescope has not provided final answers. It has provided better questions, more precise mysteries, contradictions that cannot be ignored or explained away. This is how science advances. Not through steady accumulation of facts that fit comfortably into existing frameworks, but through crisis moments when observations force fundamental reassessment. The heliocentric model emerged from the crisis of increasingly complex epicycles in geocentric astronomy. Relativity emerged from the crisis of electromagnetic theory's incompatibility with Galilean invariance. Quantum mechanics emerged from the crisis of blackbody radiation and atomic spectra. Webb has created a new crisis in cosmology. The standard model is breaking. Observations contradict predictions. Fundamental assumptions are being questioned. This is not a failure of science. It is science working exactly as it should, allowing observations to overrule theory, forcing us to build better models. The next generation of cosmology will emerge from this crisis. It will incorporate Webb's observations, explaining the universe breakers, the primordial black holes, the expansion contradictions, the coordinated spins. It might look completely different from lambda-cold dark matter. It might invoke new fields, new particles, new fundamental forces. Or it might be a subtle modification that preserves most of the standard model while fixing its failures. We cannot predict what form the new cosmology will take, but we can be certain it will be stranger, more complex, more wonderful than our current models. Because the universe keeps demonstrating that reality is stranger than our theories, that nature is more creative than human imagination, Webb's legacy will not be the specific objects it discovered or the measurements it made. It will be the paradigm shift it forced, the revolution in cosmological thinking it initiated. Future historians of science will mark Webb's first data releases as the beginning of the post-standard model era, when cosmology moved beyond the comfortable certainties of lambda-cold dark matter into unknown territory. But there is danger in this transition. Scientific revolutions are disorienting periods when old certainties crumble and new frameworks have not yet solidified. Cosmology might fracture into competing schools proposing incompatible solutions to Webb's mysteries. Research might fragment into isolated communities pursuing different approaches, unable to agree on observational priorities or theoretical frameworks. The history of physics contains cautionary examples. String theory has spent 4 decades as the leading candidate for unifying quantum mechanics and general relativity. Yet it has made no testable predictions and faces growing skepticism. Loop quantum gravity offers an alternative approach but suffers similar problems. The field has fragmented into competing paradigms without experimental guidance to choose between them. Cosmology risks similar fragmentation. Without clear observational tests to distinguish between proposed solutions to Webb's mysteries, the field might split into factions advocating modified gravity, evolving dark energy, primordial black holes, or more exotic possibilities. Productive scientific debate could degenerate into philosophical disputes immune to observational resolution. The key to avoiding this fate is focusing on testable predictions. Whatever model emerges to explain Webb's observations must make specific predictions that future observations can confirm or refute. The model must be falsifiable, capable of being proven wrong through observational tests. Otherwise, cosmology risks becoming metaphysics, an arena for untestable speculation rather than empirical science. Future telescopes will provide these tests. The next generation of instruments, launching in the 2030s and 2040s, will have capabilities that dwarf even Webb. They will observe fainter objects, achieve higher resolution, and probe deeper into cosmic history. They will map the 3-dimensional structure of the universe across vast cosmic volumes, measuring galaxy distributions, velocities, and compositions with unprecedented precision. These observations will constrain theoretical models, eliminating those that make incorrect predictions and supporting those that match observed cosmic structure. The process will be gradual, requiring decades of observation and analysis. But eventually, a new cosmological framework will emerge, tested and validated by data, commanding the same consensus support that lambda-cold dark matter achieved before Webb revealed its flaws. Or perhaps not. Perhaps the universe is too complex for any single theoretical framework to fully describe. Perhaps cosmology will remain a patchwork of models, each applicable in different regimes, none providing a complete unified description. Perhaps we will need one model for the early universe, another for structure formation, another for late-time acceleration, with no master theory connecting them. This would be disappointing, but not unprecedented. Earth science operates this way, with plate tectonics explaining large-scale geology, fluid dynamics explaining weather, and electromagnetic theory explaining the magnetosphere, without a single unified theory of Earth. Perhaps cosmic science must operate similarly, accepting that the universe is too vast and varied for monolithic theoretical frameworks. But even if complete understanding remains forever beyond reach, partial understanding has value. Webb has already delivered insights that advance human knowledge, revealing phenomena we never suspected existed. The telescope has shown us what the universe looked like when it was young. It has documented the formation of stars and planets, It has analyzed atmospheric compositions on distant worlds. These observations have practical applications beyond pure research. Understanding planetary atmospheres helps us identify potentially habitable worlds. Understanding star formation helps us predict solar system evolution. Understanding galaxy formation helps us model the Milky Way's future. Cosmology is not merely abstract philosophy. It has consequences for how we understand our cosmic environment and our long-term survival as a species. If we ever develop the capability to venture beyond our solar system, Webb's observations will serve as roadmaps. The telescope has identified nearby star systems, characterized their planets, and measured their habitability. It has revealed which types of stellar environments are hostile and which might harbor life. This information will guide our expansion into the galaxy if we survive long enough to make that expansion. But survival is not guaranteed. Webb's observations reveal a universe that is violent and dangerous. Supermassive black holes wander through interstellar space. Gamma-ray bursts from colliding neutron stars sterilize vast regions. Stellar explosions scatter lethal radiation across light years. The void is not empty. It is filled with existential threats operating on scales we can barely comprehend. Our solar system orbits the Milky Way's center once every 225 million years. During each orbit, we pass through spiral arms where stellar density is higher, supernova rates are elevated, and cosmic radiation intensifies. Some researchers propose that these passages correlate with mass extinctions on Earth, suggesting that our planet's biological history has been shaped by our galactic environment. Webb's observations of other galaxies reveal what our future holds. We see galaxies colliding, their stars scrambled by gravitational interactions. We see galaxies being cannibalized, their matter stripped away by larger companions. We see galaxies falling into supermassive black holes, their light redshifted to invisibility as they disappear beyond event horizons. In 4 billion years, the Milky Way will collide with Andromeda. The collision will take hundreds of millions of years to complete, scrambling both galaxies, structures, and likely triggering intense star formation as gas clouds collide. Our solar system will probably survive the collision intact, but it might be ejected from the merged galaxy into intergalactic space. Earth could become a rogue planet in a rogue solar system, drifting through the void forever. These cosmic timescales dwarf human history. 4 billion years is 1,000 times longer than complex life has existed on Earth. It is incomprehensibly distant future. But it is inevitable. The collision is happening right now, slowly, as gravity pulls the galaxies together over billions of years. We are watching our future approach, one observation at a time. Webb has revealed this future in exquisite detail. The telescope has observed hundreds of galaxy collisions, documenting every stage of the process. We know what happens when spiral galaxies merge. We know how supermassive black holes interact. We know what types of stars form in collision-triggered starbursts. We have a detailed preview of our solar system's far future. This knowledge changes nothing practically. We cannot prevent the collision. We cannot alter the Milky Way's trajectory through space. But we can prepare psychologically. We can adjust our cosmic perspective to accommodate the reality that our galaxy is not permanent. That everything we can see from Earth will eventually be transformed beyond recognition. This is the ultimate lesson of Webb's observations. Nothing is permanent. Not galaxies, not stars, not planets, not the structures we think of as permanent features of the universe. Everything is temporary, existing briefly before being destroyed or transformed. The universe is not a static backdrop for human drama. It is a churning, evolving, violent arena, where structure forms and dissolves on timescales that make human civilization seem like a quantum fluctuation. We have existed for perhaps 300,000 years as a species. Civilization has existed for perhaps 10,000 years. Recorded history spans about 5,000 years. The scale of cosmic time makes these durations irrelevant. If the universe's history were compressed to 1 year, human civilization would have emerged 1 second before midnight on December 31st. We are cosmic newcomers, having just arrived at a universe party that has been ongoing for billions of years. Webb's observations put human existence in its proper cosmic context. We are not the center of anything. We are not the purpose of cosmic evolution. We are a recent accident on an unremarkable planet orbiting an unremarkable star in an unremarkable galaxy. Our existence changes nothing about the universe's trajectory. We will exist briefly and then disappear, leaving no trace visible on cosmic scales. This perspective can be nihilistic and depressing. If nothing we do matters on cosmic scales, why do anything? If the universe will eventually destroy all structure in heat death or vacuum decay or singularity collision, why struggle for meaning or accomplishment? But the cosmic perspective can also be liberating. Precisely because nothing we do matters cosmically, we are free to create our own meaning. The universe does not care whether we build civilizations or destroy ourselves. We are not bound by cosmic purposes or divine plans. We can choose our values, our goals, our definition of success. Webb has given us knowledge. How we use that knowledge is up to us. We can despair at cosmic insignificance, or we can embrace the freedom it provides. We can be paralyzed by the universe's scale, or we can be motivated to make the most of our brief existence. We can see the void's indifference as hostile, or we can see it as permission to define our own meaning. The void looked back. It showed us wonders and horrors. It revealed a universe stranger than fiction, operating according to principles we barely grasp. It demonstrated that reality is more complex, more violent, and more beautiful than we imagined. But the void does not judge. It does not care whether we understand it. It does not reward our efforts or punish our failures. It simply exists, vast and ancient and indifferent, following laws we struggle to comprehend. And that might be the final truth Webb has revealed. The universe is not here for us. It was not created for our benefit. It does not exist to answer our questions or satisfy our curiosity. It exists independently of human concerns, operating on scales and through processes that render our existence cosmically irrelevant. We are pattern-seeking apes on a small planet, using mathematics and telescopes to comprehend mysteries billions of light-years away. The fact that we can do this at all is remarkable. The fact that we cannot fully do it should not surprise us. Webb has pushed human knowledge to its limits. The telescope has revealed phenomena at the edge of what physics can explain. It has documented a universe more strange than our theories predict. And in doing so, it has shown us the boundary between knowledge and mystery, the edge where human understanding fades into cosmic enigma. Beyond that edge lies the true void. Not the vacuum between galaxies, but the void in our understanding. The questions we cannot answer, the observations we cannot explain, the phenomena that defy our models. The void looked back. And it reminded us that reality owes us nothing. Not answers, not meaning, not comprehensibility. The universe exists. We exist briefly within it. We can observe, measure, model, and try to understand. But the universe does not care whether we succeed. This is the ultimate cosmic horror. Not monsters in the dark, not heat, death, or vacuum decay, but the profound indifference of reality itself to our existence and our questions. Webb has given us the most detailed map of this indifference ever created. The telescope has documented the void in unprecedented detail. And the void has looked back, revealing a universe that operates according to its own incomprehensible logic, following rules we glimpse only partially, governed by principles that might be fundamentally beyond human cognition. We are alone in the cosmos, not because there is no other life, but because we are isolated by vast distances and physical laws that prohibit faster-than-light travel or communication. We cannot reach other civilizations if they exist. We cannot escape our galaxy. We cannot avoid the collision with Andromeda or the eventual heat death of the universe. We are prisoners of space-time, confined to a tiny region of space for a brief period of time, watching the cosmos evolve around us but unable to influence its trajectory. Our observations change nothing. Our theories explain only fragments. Our existence registers not at all on cosmic scales. This is what Webb revealed when it looked into the void. Not just impossible galaxies and primordial black holes, but the ultimate truth about our cosmic situation. We are temporary patterns of matter and energy, briefly capable of observing the universe before we disperse back into the chaos from which we emerged. The void looked back, and it showed us ourselves, small, temporary, insignificant, but briefly capable of understanding, briefly able to observe and measure and model, briefly permitted to glimpse the cosmic machinery operating on scales beyond human comprehension. That is Webb's legacy. Not answers, but better questions. Not understanding, but the revelation of how much we do not understand. Not comfort, but truth. Raw, uncompromising, cosmic truth about our place in an indifferent universe. If you have witnessed this descent into the cosmic abyss, if you have confronted the truth about our insignificance and survived with your sanity intact, then prove you exist. Press the like button. Subscribe to this channel. Because in a universe this vast and indifferent, the only meaning we have is what we create together. The only significance we possess is what we grant each other. The void does not care. But we can choose to care about each other, even knowing it changes nothing cosmically. The universe looked back. Now you must decide how to respond.